We've been learning about second-order linear constant coefficient differential equations, and at this time I want to bring in the main motivation for studying that very special case. This is the primary application, and it's time for us to start talking about it. And it involves an object attached to a spring. So some of this you may remember from a physics course, but let me just review it a little bit, and it's just to give you the context, not that you have to know the physics. But suppose a spring is attached to a vertical wall and it extends out horizontally, and I know right now it's floating in air, but that's only because I haven't drawn what it's attached to yet. And let's say that a spring of course can be stretched and it can be compressed. Let's say that when it's sort of in its non-stretched and non-compressed length, that from the wall to that point, let's call that point 0 on an x-axis. So 0 is defined to be sort of the at-rest position of the spring. And actually, let me just move it over just a tiny bit, because now I'm going to attach an object, and I just want the object to be kind of centered on that 0. Okay. So if the spring is not stretched or compressed, the object would just be sitting at the 0 point. Okay. Now, we do recall from physics that Newton's second law says that F equals ma, the force equals the mass times the acceleration. So I'm just going to write ma on the left actually and put F on the right. Ma equals all the forces acting on, and I'm applying it to this object. Now, what forces are acting on here? Well, right, if the object is at 0, then the spring is not applying a force. But we can of course play with initial conditions, and we can have the objects start out here or in here, and depending on where the object is at any given time, the spring will be stretched or compressed. And it turns out that the force that a spring exerts is proportional to how much it's stretched or compressed. So in other words, if I stretch it out 1 unit, there's going to be a force pulling it back this way. If I stretch it 2 units, now there'll be twice as much force pulling it back this way. The more you stretch it, the more it wants to pull you back. So it's actually a multiple of whatever x is. And then the only other thing I have to throw in is I have to throw in a minus sign, because if x is positive, that means we're stretching, and then the force would actually be in the negative direction. And conversely, if we compress this, where the block would be at a negative x position, then of course the spring would be pushing back to the right. It would be pushing in the positive x direction. So the force that the spring exerts is always the opposite sign of what the current x is. And then k is just the proportionality constant. K is going to just be a measure of sort of how tight or loose the spring is. So that's just called the spring constant. Okay, so we definitely at least have that force. Now on the left side we have m, and of course acceleration is the second derivative of your position, of where you are. So that's why F equals ma always leads to naturally a second order differential equation. And then let me just say there may be other forces involved, and we do want to identify some other forces that may be involved, but the first one, the main one, which is based on the whole setup, is that we do have a spring, so we have this spring force. By the way, that's called Hooke's law from physics. Hooke's law is the force that a spring exerts. Okay. Now let's talk about those other forces. In real life we would have friction for the surface that this object is sliding on. Let me just call it little f, and then let me just denote it as friction underneath. Okay. And I left space because there's another one that I want to talk about. There might also be, well, some sort of damping force or resistive force. Now, if this is just in air, then there would be some air resistance, as if this thing sort of moved back and forth. As this thing moves, anything that moves in the atmosphere has some air resistance. But we could also apply this to something like if this is in a liquid, if this is in water or in oil, it might be a stronger resistive force. And what we want to use there is, it turns out that through experiments, resistive forces tend to be stronger the faster you are going, right? So think of sticking your hand outside of a moving car's window. And if you're going really fast, you'll feel a really strong force on your hand. If you're not going very fast, it won't be very strong. So one model for this is that it is proportional to your speed, v. But of course, v is the first derivative. Okay, so this is resistance of some sort. In this context, we're going to call it a damping force. All right, and it's a little bit different than friction. Friction is kind of a damping force as well, but friction would be constant, whereas this kind of resistance that I'm talking about would be based on speed, and so it involves the derivative of x. Okay, and then finally, I'm just going to throw in maybe there are other forces that we might add in later. So maybe there's a additional force that we're adding in, like a driving force. So maybe we're pushing this thing manually, right, back and forth, back and forth. Or maybe there's a wind that's, so this is beyond the air resistance, but there's wind that's sort of pushing this all the time. You can also have situations, again, not to get too much into physics, where maybe this thing is will react to magnetic fields, and maybe you have a magnetic field that like pushes it this way, then this way, then this way, then this way. So yeah, there are all kinds of ways that you can just sort of add additional forces onto this. So we'll just group those all together at the end here. All right, so these are all the possible forces that we could have on this object. Now the first two that involve x and the first derivative of x, I'm going to bring to the other side. Just fast forward there. Okay, so yeah, so all the x stuff is on the left-hand side, and then we have this other stuff which would either be constants or would be time dependent. It would be dependent on t, but it would presumably not be based on x. Okay, so this is kind of a nice standard form for a second-order differential equation, and we see that it is the kind that we've been studying. It's linear, and it's constant coefficient. M, B, and K are our coefficients. Now, one thing I'll note is that M, B, and K, these would all be positive numbers, right? Mass is certainly positive. K, the spring constant, would be a positive number. We kind of built the negative into the formula already, so the K itself would be positive. And the same with B, by the way. The B would be, we built the negative in for the fact that the air resistance will be in the opposite direction that you're moving in. So the negative's already there, so B would be a positive. So M, B, and K are positive constant coefficients. So it's actually slightly more special. It's constant coefficient, but we only have positive constant coefficients. All right. And then it's not homogeneous in general, but it could be homogeneous if we assumed there was no friction and we assume there were no other forces. So it could be 0, possibly, if we make those assumptions. Like that's one scenario we could investigate. 0 or, we would say like negligible friction, really, really smooth surface, maybe ice or something. Of course, in reality, everything has at least a little bit of friction, but let's say it's negligible, 0 friction, and nothing else is pushing or pulling it in any way. Then we would be homogeneous. Okay. So this is the case, this is the scenario that we can apply what we've been learning to. We will later look at the non-homogeneous case when we have friction or other forces to deal with, but we already can deal with the homogeneous case where we assume friction is negligible and there are no other forces. One more thing before moving on is we've been assuming there was always a 1 in this position, but we know we can deal with that, whatever our equation is, whether it's 0 or not on the other side. We can divide through by m if you want to. You don't have to, but that is a possibility. We could rewrite the left-hand side like this, and then we have a 1 here, a constant here, a constant here. Those constants would still be positive. Okay, so using what we know about these kinds of differential equations, let's analyze the situation in 4 different cases. So again, no friction or other forces, so we do get homogeneous, but we are assuming, of course, the spring is there, so there's the spring force. And, well, in general, we're going to assume that there's this damping force as well. But actually, the first case I want to talk about is if B is 0 and we don't have any damping. So the undamped case. So this would look like this. Now, of course, I could bring the kx over equals negative kx. And we can solve this using the characteristic equation, but actually we solved this in a different way before we learned about the algebraic equation approach. We just came up with a decent guess for this differential equation. And I guess I should divide by m as well to make it really obvious. So just to remind you, we're asking for a second derivative of a function to be a negative number times the function itself. And if you recall, we thought about this and we realized the answer is cosine and sine will both work. If you take 2 derivatives of either cosine or sine, you'll get back to where you started with a negative out front. And if you fit in the right coefficients, you can get whatever number here you want. So yeah, it turns out to be a general solution that looks like that, just a cosine and a sine. Notice no exponential term. And so what that means is the behavior is, well, it's what you would expect. You would get whatever the initial condition is. We'd be starting somewhere, but we're just going to get something that oscillates forever. And because we don't have an exponential term that's making this either die out or grow, it's just going to keep the same amplitude the whole time, right? And that makes sense because your object that's attached to a spring would just go back and forth forever. And if there's no damping and no friction, what's going to stop it? What's ever going to slow it down? Nothing. So we just get ongoing oscillations in the undamped case. I can write it in the other format where I do c cosine of root k over m t minus delta. And again, it's the same graph, it's just writing it algebraically in a different way. And then we can really identify the amplitude. And remember the amplitude, this c can be connected back to the a and b by, it was the square root of a squared plus b squared. So that's your amplitude. And your period of oscillation, the amount of time it takes for the block to move through one full cycle, sort of back and forth once, right? That'll be 2 pi divided by this number, the square root of k over m. And so you see that how fast it moves back and forth, how much time it takes, depends on both how big it is, the m, and how tight the spring is, the k. If the spring is really tight, we'll have a bigger k here, and you can see that'll make this number overall smaller. So a tighter spring will move faster. That makes sense. But on the other hand, if we have a bigger mass, if we have a larger object attached to the spring, that's in the denominator of the denominator, so that'll actually make this whole thing bigger if we have a bigger m. So bigger mass means bigger period. That means it will take longer. So larger objects will kind of go a little bit slower. So that all makes sense, and there's the formula for the period. Well, I should say, I haven't really given you a formula for the amplitude because the c, either in terms of the c or in terms of the a and b back here, they would have to be determined by the initial conditions. How far out the block will stretch back and forth will be dependent on how you started it, whether you pulled it really far out and let go, or whether you just started by giving it a push, and then how hard a push you gave it will determine how far it goes. It's extreme, how far it goes, how extreme it gets, either compressed or stretched. So that'll be based on the initial conditions. In fact, let me just denote that here. The amplitude would be totally based on your initial conditions. The period is not, which is interesting. How fast it goes actually is not determined at all by the initial conditions, because this formula here is only based on the k and the m, which are the physical things that we started with. Okay. Let's move to the second case. Now, in the second case, let's assume we do have a B. We do have damping. We do have non-negligible air resistance. And in fact, let's assume that B is big enough so that we get two real solutions. Now, let me just remind you that the way we would attack this now is we would go m lambda squared plus b lambda plus k, set it equal to 0, and we would solve that, right, and get our well, either 1 or 2 lambdas, and they may or may not be complex, right? That's how it broke down. Let's assume right now that we get two real solutions. Now remember that what that would mean is the thing in the square root would be coming out positive, b squared minus 4mk, and then it'd be all over 2m. So right, so we're saying b squared minus 4mk would be greater than 0. In other words, b squared is greater than 4mk. So the b is big enough. I guess I can go one more step and take the square root. B is bigger than the square root of 4mk. B is big enough compared to the m and the k that we get two real solutions. So there's enough damping for that to happen. So we actually call this the overdamped situation. And of course, what that would mean is we would get two exponentials. Right? That's always what happens when you get two real solutions. And furthermore, let me just point out that m and k and b are all positive, right? So m and k are positive. So when we have b squared minus 4mk, that's going to be less than b squared because we're subtracting a positive amount. So what's inside the square root is less than b squared. So if you take the square root, it's going to be less than b. So this square root is less than b. So now we have a negative b, and now for the minus sign, of course, that'll just be that'll be even more negative. So that when we pick the negative, we will get that lambda will be a negative lambda. But even when we pick the positive, again, I said the square root would be less than b. So we have a negative b plus something that's positive but less than b. You see that the negative b will win out by a little bit, and that one will be negative as well. Okay, rewind that and listen to that again, or think about it for yourself. But my point is that because m, b, and k are all positive, both of these answers, these two real solutions, are going to be negative. That has to happen in this case. Okay, so the lambda 1 and the lambda 2 are negative numbers. So what that means is that we are going to get the decaying kind of behavior. Okay, so I don't know, this may be surprising to you, but what we're saying here is that if we, let's say that's the relaxed point of the spring, and let's say we stretch it out, and then we let go. Normally we think of a spring as they would go back and forth, but if it's over damped, if there's a lot of damping, if there's a lot of resistance compared to the k of the spring and the m of the mass, defined by this little inequality right here, then actually what will happen is this thing will start moving in, but it'll slow down, slow down, slow down, and just kind of creep towards 0. Right? That's what this says. Over time, the x will just kind of creep down towards 0. So this guy will just creep down here. It actually will not pass the 0 mark. It won't go past and then come back. There's too much damping. It never gets up enough steam to go past and then have to come back. So this is the overdamped situation. And it happens when this is true. Okay, moving on. Of course, the next case is where we get one real solution. B squared minus 4mk equals 0. right? So the thing under the square root equals 0, so we only get one answer when we look at our m lambda squared plus b lambda plus k equals 0 equation. We get one answer. And in fact, what we get is, right, if the quadratic formula, the square root part is 0, we would just get negative b over 2m, right? The plus or minus part would not be there because it would be 0. And our solution, right, is a e to that lambda plus b t times e to that lambda. Now this one's easier to see. This lambda is obviously negative. B and m are positive, but there's a negative right there. So this guy is negative. So we have a negative exponential and then t times a negative exponential. We saw before that this again kind of dies down. It follows this. Both of these are negative exponentials, so even the t itself won't necessarily do anything. I should say what it might do is actually go up a little bit first and then go down, depending on the initial conditions. That's possible, but it's going to just die down in the long run. The negative exponential is going to win out. And again, what we have here is that it's not going to, if we stretch it out and let go, it's not going to go past its resting point and then come back. It's just going to slow down. But we're right at the edge, right? It's kind of over. If you looked at this in real life, you might not be able to tell the difference between critically damped and over damped. You might not be able to tell the difference, but critically damped is right on the edge of not going past it. It gets really close. If there was just a little bit less damping, it would have passed and done a little bit of back and forth stuff, but it does not, right? So it just dies out. Okay. And so finally, and this is of course the case where it does go past its original point, when b squared minus 4mk is negative, we get the two complex solutions because the square root in the quadratic formula will be negative, and this is considered underdamped. So our solution in this case will look like a e to the alpha t cosine beta t plus b e to the alpha t sine beta t. Or we could write it as c e to the alpha t cosine of beta t minus delta, sometimes a more useful form. And what this will look like, as we saw before, is it will oscillate because we do now have a trig function. We have the cosine. But unlike the undamped case where it just oscillates forever, this oscillation will die down over time because of the exponential, right? So that exponential is sort of forcing these oscillations to die out. And that's what we get. So this is the case where quickly drawn spring doesn't look very good. Here's the 0 point. We stretch it out, we let it go. This thing will go back, and then it'll come back here, and then it'll go here, and then here, and it'll just excuse me, oscillate back and forth. But because of the air resistance, it's going to slow down eventually and come to a, well, technically it never comes to a standpoint, but eventually, pretty soon it gets to a point where no device could measure any detectable motion, right? So you might as well call it stationary at that point. All right, so these are the four cases: the undamped, the overdamped, the critically damped, and the underdamped. In a way, maybe I should have done underdamped last, undamped last, because that's really that's closer to underdamped. So maybe I slightly did this out of order. But hopefully you see the situations, and of course what I would want you to do is to be able to know which case you're in and identify which one it is and write down the solution, understand the behavior. And I apologize, I keep fixing the typo on each page. I had b greater than 0 in the overdamped case, but every time it should have been b squared minus 4mk is greater than 0. B would always be greater than 0 in all cases, but it's b squared minus 4mk which is the important quantity. So I hope I fixed that on each page there. Yeah, b squared minus 4mk is the critical thing in each of these cases to look at. Okay.